Let's return to the example of a temperature function that changes at a rate in time of -2 degrees per second at the time when whatever time the temperature is 150 degrees. Okay, so a temperature of 150 degrees, implicitly we're talking Fahrenheit here, is going to give us a rate of -2 degrees per second. You recall that we set up the proportionality equation in assuming a room temperature of 80 Celsius, 80 Fahrenheit, that was dt over dt equals k times t minus 80. Substituting the information we have here into that function, we obtain k equals -2 over 70 degrees per second per degree. And that's -0.028 degrees per second. And I've got per second here. And that should be per degree, right? And this should be per degree. It's difficult to write at this angle, so forgive the handwriting. Very inconsistent with units there. I don't know what I was thinking about. Anyhow, we end up with the differential equation dt over dt equals -0.028 degrees per second times t minus 80. This equation allows us to determine the rate at which the temperature changes if we know the temperature. Now let's say that we know that at clock time t equals 0, the temperature is 150 degrees. We can use this equation if we didn't already know it. If we didn't already know what the rate was, we plug 150 in here and multiply this out, and we end up with -2 degrees per second. If we want to predict the temperature at 5-second intervals, 0, 5, 10 seconds, we're going to take a time interval of 5 seconds, and we're going to ask ourselves, well, at -2 degrees per second over a time interval of 5 seconds, how much change of temperature do we have? The answer to that's fairly obvious. At -2 degrees every second, then in 5 seconds, temperature is going to change by -10 degrees. That's going to bring the temperature down to 140 at the t equals 5 mark. Now we'll note that this is only an approximation. We've used the rate of temperature change at 150 degrees and assumed that this rate stays constant all the way down to temperature 140, and we know that's not the case. We know that as temperature declines according to this equation, the rate is going to decline. However, we're not going to worry about that. We're just going to keep it in mind that that's something that's going to make our approximation here inaccurate, and we'll see later what we can do about that. But anyhow, t equals 5, we assume the temperature now is 140. We plug 140 degrees back into this equation and we get -1.68 degrees per second. Over 5 seconds, that's going to give us a temperature change of -8.4 degrees, which 5 seconds later here at the t equals 10 mark gets us down to 131.6 Celsius, or Fahrenheit. And we then plug the 131.6 into the equation that gives us the rate, and we see that the rate is -1.44 degrees per second. Over 5 seconds, that's going to be -7.2 degrees, and then we can figure out the temperature at 15 seconds, and so forth. And we can obviously continue this process as long as we wish. Now, the verbal assignment was to extend this process till the temperature is less than 100 degrees. I think that takes about 8 or 9 steps. And then to recalculate the temperature at the 5-second interval, starting at t equals 0, but using a 1-second increment. So we have to make 5 calculations to get down to the 5 seconds if we use a 1-second increment and recalculate the rate at each time.